Hello everybody, welcome into another lesson. So today we are going to graph systems of quadratic inequalities. So yesterday we graphed quadratic inequalities in general. Today we are going to graph systems of quadratic inequalities. So here you have y is greater than or equal to x squared, and then y is less than or equal to x squared plus 3. When you're approaching a system, you want to graph each of these individually. So let's say, for example, here we have, let's start with y is greater than or equal to x squared. Well, it has the equal to component, so it's going to be a solid parabola, right? So draw yourself a solid parabola through y equals x squared, so that we know it would have a vertex at 0, 0. And then you would have points 1, 1, 2, 4. And then on the other side, you'd have negative 1, 1, and then negative 2, 4. So go ahead and draw your solid parabola there. Alright, so next, we also have y is less than or equal to x squared plus 3. Well, again, we have the equal to part, so this will be a solid parabola through y equals x squared plus 3. So the vertex in this case is at 0, 3. You would end up having the coordinate 1, 4. Then you would have 2, 8. Which would go right there, and then you would end up having a negative 1, 4, and then negative 2, 8, which would go right there. And then just draw your parabola through those points. Got a little off-keter there. And you notice these two parabolas really don't intersect. Points of intersection between the two parabolas also help to know that. Now, once you've drawn both of your parabolas and you've ascertained whether they're solid or dotted, depending upon being equal or not equal, now it's time to shade the region that fits both criteria. So we want to shade the region where y is greater than or equal to x squared. Well, that's going to be inside the parabola, right? That'll be above the parabola line. So it would look like you're shading everything above y equals x squared. However, we have the other parameter that y is less than or equal to x squared plus 3. So it's going to be above the first parabola but below the second parabola. So you're literally going to shade everything between the two parabolas. Everything between the two parabolas is the solution to this. That would be the region that you would shade. Everything between the two parabolas would give you the desired region you're looking for. So that's the region that represents y is greater than or equal to x squared, y is less than or equal to x squared plus 3. And I got two more examples here. Let me just redraw this axis a little bit here. Draw my coordinate plane a little bit here. All right. Let's do this. So what's next? We have y is simply less than negative 3x squared. Then we have y is greater than or equal to negative half x squared plus 5. So y is just less than negative 3x squared, but y is greater than or equal to negative x squared plus 5. Well, a couple of things here. Remember yesterday we did a lesson on solving systems of quadratic equations? Systems of quadratic equations. That principle kind of comes into apply here. We want to get any points where these two quadratic equations, where these two parabolas would possibly intersect. So you're going to treat these as if they're equal for a second. So take that negative 3x squared, set it equal to negative half x squared plus 5. So then you would end up getting, let's see, negative 3x squared plus the half x squared. We're definitely going to be solving by square roots here. So negative 6 halves x squared plus 1 half x squared would be negative 5 halves x squared. Would end up equaling 5. Well, you can notice right away you're going to have an imaginary solution, meaning that these two parabolas really don't intersect. They don't intersect at all. Because if you have an imaginary solution for x, that means that they're not going to intersect. So we don't have to worry about points of intersection. Now, what we do need to worry about, however, is the parabolas themselves. So this case, we have y is just simply less than negative 3x squared. Well, we know it's going to be an upside down parabola because the coefficient on x squared is negative. The vertex would still be at 0, 0. We'll just put a little dot there. And since it's just less than, you're going to have a dotted parabola to indicate that the parabola itself is not part of your solution. Let's find another point. If I take negative 1, I would get y is at negative 3. So right here, if I take negative 2, that'd be 3 times 4, which would be negative 12. 6, 7, 8, 9, 12, which would be about right there. And then if I did it with positive values, I would end up getting 1 negative 3 and then 2 negative 12. And then I can draw a dotted parabola through those points, since the parabola itself is not going to be part of the solution. All right. Now, so I've done the dotted parabola for y is less than negative 3x squared. Now, let's draw the parabola for y is greater than or equal to negative half x squared plus 5. This time it will be a solid parabola. And on top of that, you're also going to want to find your vertex, which would be at 0, 5. So that's going to be all the way up here, 0, 5. And then let's find some x-intercepts if we can to aid us in drawing this. So let's see, so negative half x squared would equal negative 5. Multiply both sides by negative 2. You would get x squared equals 10. Giving you x-intercepts at plus and minus the square root of 10, 0. So you'll have two x-intercepts. That would put you a little over 3. So a little less than negative 3 and then a little more than positive 3. Now you connect your dots and you draw a nice solid parabola. And what do you got here? You have a nice fat parabola there. So you see these two parabolas don't intersect. Now, we have to figure out y is less than negative 3x squared So that would be below the parabola, right? That's going to be below the parabola. And then you're going to end up having y is greater than or equal to negative half x squared. So that'd be above this parabola. But you need to find the region that fits both. Unfortunately, there is no region that fits both. So there's really no solution that meets this. We have no solution because you would have y is less than negative 3x squared. You would shade, of course, below this dotted parabola, which would be inside of it. But that would violate the y is greater than or equal to negative half x squared because that would be above the parabola. So you need to find the region that meets both solutions, and there just isn't one. I mean, there simply isn't one. So sometimes you will have that when you're graphing these. There's no region that meets both criteria. All right, one more. What if we have y is greater than or equal to x squared plus 2x plus 1, then we have another y is greater than or equal to x squared minus 4x minus 4. Well, let's worry about here. Let me make sure I got the inequalities right. Yes, okay. So both of these are greater than. So y is greater than or equal to x squared plus 2x plus 1. Y is greater than or equal to x squared minus 4x. This should be, my bad, this should be x squared minus 4x plus 4. Okay. We need to, of course, find the region that meets both qualifications. Well, first thing I would do, treat this like a system of equations. Find any points of potential intersection. So x squared plus 2x plus 1 you'll set equal to x squared minus 4x plus 4. This will really help you get any potential points of intersection. Now let's make the right side equal to 0. So that would look like 6x minus 3 equals 0. So you get rid of the quadratic term, which would give you 6x equals 3, x equals 1/2. So you get a value of x equals 1/2. Now stick the 1/2 into any of these equations. Pick any equation, so you'll end up having, see, 1/2 raised to the second power plus 2 times 1/2 plus 1, well, that's going to equal, of course, 1/4 plus 1 plus 1, which would give you 1/4 plus 2, which would give you a y value of 9/4. So they intersect, the two parabolas would intersect at the point 1/2, 9/4. That does come in handy when you're graphing these. That helps you draw an accurate graph. Now, we know the points of intersection, so let's plot 1/2, 9/4, which would be like at 1/2 and 2 1/4 in the y. That would be right about here. There's that magical point of intersection that both parabolas should pass through to intersect. But what we need to do now is figure out the graph of each of these individual parabolas. Well, they're both equal to components, so they're both solid parabolas. Well, x squared plus 2x plus 1, notice that's a perfect square trinomial. That would factor into x plus 1 squared equals 0. That means your x-intercept and your vertex both are going to be at the point -1, 0, right? They will be at -1, 0. So here's your vertex and the x-intercept, and it only touches the x-axis because the factor is raised to an even power. Remember, if you even touch, it'll just touch. If this were to the first power or third power, it would cross through the axis. So we can roughly draw this parabola. Now let's pick some other points. If I pick x equal to 0, I would get 0, 1. If I pick 1, I would get, so let's see, 1 plus 2 is 3 plus 1 is 4. I would get the point 1, 4. So I have enough information to draw the parabola this way. Now let's pick -1. So obviously, if I put -1 into this, I would just get 0. Well, that's already the vertex. How about -2? -2 plus 1 is what? -1 squared is 1. So I would end up getting the point -2, 1. If I put in -3, well, -3 plus 1 is -2, raised to the second power is 4. So now I can completely draw this parabola. There's my x squared plus 2x plus 1 parabola. Now I need to draw my other one. So this x squared minus 4x plus 4, that's also a perfect square trinomial. It's going to factor into x minus 2, that quantity squared equal to 0. And this will be another solid parabola because you have the equal to component. Well, both the x-intercept and your vertex are going to be at x equals 2. So at 2, 0 is the vertex. So here's my vertex. Now let's go to the right. What if I put in 3? 3 minus 2 is 1, so I would have the point 3, 1 right here. If I put in 4, 4 minus 2 is 2, raised to the second power gives me 4. So the point 4, 4 would go there. I have enough to draw the parabola this way. Now let's do to the left of the vertex. If I put in 1, 1 minus 2 is -1, that would give me positive 1. So 1 would give me 1. If I put in 0, 0 minus 2 is what? -2 raised to the second power is 4. I'd have the point 0, 4. And notice here's the point of intersection. So you see now where these two parabolas intersect at that point 1/2, 9/4. So we got two parabolas side by side. So here's the question. What region satisfies both of these? Y is greater than or equal to x squared plus 2x plus 1. That's going to be inside the parabola, right? Because outside of it would mean it's less than it would be less than, y would be less than the value of this quadratic equation. So we're definitely going to be inside this red parabola here, your first one. Then we also have y is greater than or equal to x squared minus 4x plus 4. It would also be inside the purple parabola, right? However, you can't consider the portion to the right of the red line, to the right of the first parabola, because that would make it y less than that first equation. So the region that meets both qualifications is this area in between the two parabolas after they intersect. This region right here would meet both qualifications. Literally, if you just shade that region, that is the region that meets both qualifications for this system of quadratic inequalities. So much like linear inequalities, you just find the region that would meet both qualifications. And oftentimes you not only want to find each parabola individually, solve for your vertex and x-intercepts, you also want to solve it like a system of quadratic equations and find any points of intersection where the two parabolas intersect, so you get an accurate picture. And then you draw your two parabolas, shade the region that meets both qualifications, and you're done. So that's it for this lesson. There is just one more lesson left in the quadratic equation unit, and that's going to be modeling with quadratic functions. So I hope everyone has a great day. Take care.